Okay, we're going to take a look today at chapter 18. Let me see, I'm going to pin my video so it makes it bigger. There we go. And you guys will have to get all the documents from Brightspace. But this is our last chapter. Once we finish with this one, today we'll have a lecture. Thursday we'll look at the review document. Following Tuesday, a week from today, we'll have an exam. And then we'll get into reviewing for the final. And there's also a review document in Brightspace for the final. The difference is it does not have worked problems with it, because most of the problems in there you've seen before, and it's basically a review. But we'll work from that document to get you ready for the final. Okay. Any questions, problems before I get started? Nope. All right. Let's take a look at redox reactions. It helps if I turn this thing on. There. There we go. This is a reasonably short chapter, but some of the concepts might be a little strange. So we can sort of pace ourselves, take time. First of all, what is a redox reaction? Redox is short for oxidation and reduction. We say redox because it sounds better than oxide. But anytime you have a redox reaction, or you suspect a redox reaction, you look for a transfer of electrons. If electrons are transferred between reactants, then you have a redox reaction. And there are special characteristics that are unique to the redox reaction. Some of them ultimately leading to things like batteries. This example is just showing the reaction of sodium metal with chlorine gas. And you'll see that we're transferring electrons from the metal to the non-metal. And that's typically the way it goes. When you have a metal and a non-metal reacting, the transfer is from the metal to the non-metal. Now, you don't have to have a metal non-metal to react in a redox fashion. You can have two non-metals reacting, and I'll give you some tools in a few minutes that'll help you determine whether you do have a redox reaction, because all reactions are not redox, and it's important to recognize, to figure out which ones are and which ones aren't. But in this case, sodium transfers electrons to chlorine, and that's why when you have table salt, sodium chloride, you have a crystal lattice composed of sodium ions and chloride ions. And they are complete ions. Sodium has lost an electron, chlorine has gained an electron. And that's characteristic of all redox reactions. If one side loses electrons, the other side has to gain the same number. Okay. Oxidation is, by definition, a loss of electrons. When something is oxidized, it is losing electrons. So in this case, sodium is oxidized. Reduction is a gain of electrons. So anything that's reduced, in this case chlorine, chlorine has been reduced by gaining electrons. And I'll show you on the next page a little mnemonic device that'll help you remember those two. It's called, here you go, oil rig. O stands for oxidation. Oxidation is loss, and reduction is gain in reference to transfer of electrons. Okay, so if we have this situation where we're looking at a tin 2+ ion reacting with an iron 3+ ion, we end up with a tin 4+ ion and an iron 2+ ion. So this is the way I like to diagram these things. If I write that one and this one, and this reaction is balanced for us. And notice these are all positive, these are all cations. So what's missing? The anions are missing. And the anions are missing because they're spectators. You don't need them to discuss this problem. So it's not that the reaction is a net positive charge all the way through, it's that we're just not showing the negatives. And then we have this as a product and this as a product. Okay, so the way I like to diagram these things is to show the path of the electron transfer. If we're going from this tin to that tin, how did we get there? Remember, anytime you create an ion, you do it with electrons. You either add electrons or lose electrons. So if we're going from a 2+ to a 4+, we had to lose 2 electrons, 2 negatives. If we lose 2 negatives, that makes us from 2+ to 4+ an extra 2 positives, which are protons. Right? Protons in the tin nucleus account for that extra 2 pluses. So we lost 2 electrons for each tin. For each tin. And since there's only one tin, that means 2 electrons were lost from tin total for this reaction. That means that they had to go somewhere. Right? So in order for iron to go from 3+ to 2+, it had to gain 1 electron, which neutralized one of those positives. And now we only have 2 pluses. So this one is a gain of 1 electron per iron, but we have 2 irons, see? Which means 2 electrons. And that accounts for the electron balance in this reaction. Okay, so in this reaction below, tin 2 is oxidation is loss, is oxidized. Okay? Now, we're going to need a way of tracking the electrons because you don't always have clear-cut charges to deal with. Sometimes you've got to deduce a potential charge. We use a bookkeeping scheme. It's called Oxidation States. And we need a few rules to go by. It's important to recognize that this bookkeeping scheme does not always mean that you're dealing with ions. It's just a way to track electron movement. And we treat the various reactants and products as if they were charged, recognizing that they may not be. Now, some of them could be charged, just like our previous example, but they don't have to be charged. Just keep that in mind. This is a bookkeeping scheme so we can follow the movement of electrons. So we need some rules. First rule, the oxidation state of any atom that's an elemental state, such as if 10 were not charged, it would be Sn. That would be zero oxidation state. And we put the oxidation state up here where the charge would normally be, just to keep track of things. We can say this for under standard conditions. This would be elemental oxygen. And the oxidation state on each one of those oxygens is zero. We could even have sulfur in its elemental state. Each one of those sulfurs is zero. And we got 4 of them. Right? So 4 times 0 is 0. So the whole thing is 0. Okay, that's the first rule. That's the easiest one. Second rule. If you do have an ion, then its oxidation state is the charge on the atom. And our previous example was that rules across the board. All of them were ions. So all we had to deal with was the charge as the oxidation state. Whenever you have oxygen in a compound, we treat it as a -2 oxidation state. For instance, water. This would be a -2 oxidation state for that water. Okay? And since the whole compound is neutral, the hydrogen should be a +1. Because 2 times +1 is +2, balance is -2. The exception to this oxygen rule is if oxygen is bound to another oxygen in what we call a peroxide. If it's bound like this, and it can have anything else attached to it, right? This whole group is -2. So that means each one is -1. Okay? That's the exception for oxygen. All right. Hydrogen. We deduced hydrogen for water. But if hydrogen is in any covalent compound, that is, it's bound to any other non-metal, it will be a +1 charge. Oxidation state, excuse me. Oxidation state for hydrogen is +1. If hydrogen is bound to a metal, then it will be a -1. For instance, if we have aluminum hydride, right? In that case, aluminum is a 3+, and hydrogen is a -1. Right? But if hydrogen is bound to a non-metal, it's +1. It's bound to a metal, it's a -1. I'm not sure if the -1 rule is given in here, so that's why I'm throwing it in here to show you the difference between hydrogen in the 2 different types of compounds. Fluorine. If fluorine is in any compound, it doesn't matter what it is, fluorine is always taken as -1. No other options. When you've assigned oxidation states to all the atoms in a compound, then if it is a compound, a neutral compound, then all of the oxidation states must add up to 0, to neutrality. So if you have an oxidation state on an element, and there are more than one element there, you have to multiply that oxidation state times the number of elements. before you can add them together with the others. And so each symbol has its own oxidation state. If they're multiples, then you have to multiply by the number of them. And when you add them all up, they have to be equal to 0. If you have a polyatomic ion, then all the oxidation states have to add up to the charge on the ion. If you're looking at the first column of elements, the alkaline metals, they're always +1 oxidation state. And the alkaline earths, their next door neighbors in the second column, are +2. I think I left out aluminum. If aluminum's in there, it's always +3. Okay, let's see if we can use these rules and answer some questions. What are the oxidation states for each of the elements in this compound? K2Cr2O7, which is potassium dichromate. Okay, so working from left to right, potassium is an alkaline metal, so it's a +1. Oxygen is, oxygen is -2. Right? It's not a peroxide, so it's a -2. Then we can deduce the chromium oxidation state. So we say this one is +2 total, 2 times +1. 7 times -2 is -14. Right? So what do we have with these two? These two are -12. That means that chromium, those two chromiums, must balance the -12 with a +12. So a +12 for these two means that each one has to be +6. Okay? And you can check yourself to see if they all add up, right? +2, -14, let's see, +2 and +12 is a +14, -14, we balance. That's neutral. How about this polyatomic ion, which is carbonate? So this oxygen has to be a -2 times 3 is a -6. But we have to hold out 2 of those negative charges for this. Right? You've got 6 here. So really, you only need to neutralize 4 of them. Right? Because we saved 2 for that charge. So we have -4 that needs to be balanced with this one carbon, which has to be +4. And you can check yourself, right? 3 times -2 is -6, and +4 is a -2. So we're good. That's the charge on the polyatomic ion. Okay, manganese dioxide. This one should be fairly easy. Actually, that's not a complete name, is it? Because manganese has the potential for several charges. So we have to find out what is the oxidation state or the potential charge on manganese to name the compound correctly. So this is a -2, -4 total. That means this has to be a +4. So the name would be manganese 4 oxide. Okay. PCl5. Go. Now, we don't have a rule for this one, do we? We have one for fluorine. So we've got to make a choice. Fluorine and chlorine are in the same family. And if we give chlorine the same charge as fluorine, the halogens, then we can proceed. Otherwise, we're stuck because phosphorus doesn't have a standard oxidation state. Chlorine is, if it's an ionic compound, it would be a -1. So that's where we have to start. And it's okay to do that because, after all, this is a bookkeeping scheme. We're not saying that chlorine is a -1 ion. We're just saying that its oxidation state is -1. And that's not splitting hairs. That's just practical. We've got to do that. Otherwise, we're stuck. So if we say chlorine is like fluorine with a -1, that means -5 for chlorine, +5 for phosphorus. Okay. Now the next one is fairly straightforward because we do have a rule for fluorine. SF4. And since both of these, I should have named the previous one, phosphorus pentachloride, because they're both, this is a type 3 compound for naming purposes. This is also a type 3. So this would be sulfur tetrafluoride. And it's a -1 oxidation state, -4 total, +4 for sulfur. There we go. All right. What's next? Okay, we've seen that reaction before, haven't we? What are the oxidation states on each one of these? Well, we saw the original slide. The oxidation states, to begin with, for this one, that's an element, right? It's 0. That's an element, 0. Over here, you have a chlorine. Actually, it'd be safer to start with sodium because sodium has a rule. Sodium is +1 always. So that makes chlorine -1. Okay. Let's see. I don't want to steal my own thunder, so let me check something. Yeah. Let me put this one on the board. And that's a solid. Okay, so we determined this one was 0. This one was 0. This one was +1. This one's a -1. So if we go from sodium metal to sodium ion, what happened? We lost 1 electron. To go from a 0 to a positive, we have a loss of 1 electron per sodium, but we have 2 sodiums. Equals 2 electrons lost. That means chlorine had to pick up the electrons with a gain. Gain 1 electron per chlorine. Times 2 chlorines, right? 2 equals 2 electrons. Okay? So sodium was oxidized, chlorine was reduced, and those 2 processes always occur together. You cannot separate. That makes sodium is the agent of reduction for chlorine. In other words, sodium causes the reduction of chlorine. That makes sodium the reducing agent. right? And conversely, chlorine causes the oxidation of sodium. That makes chlorine the oxidizing agent. Okay. All right. Now we have an example. There are no metals in this reaction. These are all nonmetals. We can still use our bookkeeping scheme. Let me see what the questions are. Oh, okay. We got to say what's what. All right, let me move down a little bit so I can CH4. I'm going to leave out the phases because they're all gases. 2 oxygens and a carbon dioxide and 2 water. Okay. So what are the, let's do the oxidation states on everything first. This is an element, 0 oxidation state. This is, hydrogen in this case is combined with a nonmetal. That means it's a +1 or a +4 total, which makes this carbon -4. Okay. This oxygen is a -2, which is a -4 total. This carbon is a +4. So that carbon has gone from a -4 to a +4. This oxygen is 0 here, but over here, it's -2. This is a +1. Okay, so what's happened? Well, the carbon is oxidized. It had to lose electrons, right? To go from a -4 to a +4, we had a loss of how many electrons? I like to keep things straight. If I've got to go across the 0 mark, if I got to go from a minus to a plus or a plus to a minus, I work my way to the 0, and then I go from the 0 to the next level. So from here to 0, you had to lose 4 electrons. But from 0 to +4, you had to lose 4 more electrons. So we actually lost 8 electrons per carbon. And there's only 1 carbon in this balanced equation, equals 8 electrons total. Okay, so if that's what happened to carbon, where did those electrons go? The carbon was oxidized, so that makes it a reducing agent. It had to reduce something. So what got reduced? It looks to me like oxygen went from 0 to -2. And it also went from 0 to -2 here. In other words, oxygen went 2 ways. So here's what I would do, like that, and then like that. So to go from 0 to -2 would be gain 2 electrons, and then here you would also gain 2 electrons per oxygen per oxygen. Here you have 2 oxygens equals 4 electrons, and here you have 2 oxygens is 4 electrons, which together is 8 electrons, just like that. There. There. So we've accounted for all the electrons. That makes methane the reducing agent, and oxygen is the oxidizing agent. We should have done this animation up here first, and then done this part. I need to switch those around. Okay. Okay. Just a little review. Characteristics of redox reactions. The one defining characteristic of redox is transfer of electrons. You can transfer electrons to form ions, that's possible. Or you can transfer among elements in compounds that do not form ions. In other words, they're in covalent compounds. And oxidation is loss, oil. Oxidation is loss, which does what to the oxidation state, the oxidation number assigned to that state. You increase the oxidation state when you lose electrons. That means it becomes more positive. It may move from one negative to the next, but it's becoming more positive. It's moving to a smaller negative if it's becoming more positive. And then it may even go into positive territory like our carbon did. Oops, went backwards, sorry. And when something is reduced, its oxidation number is decreased, becomes more negative. All right. Now we've got a mix of reactions coming up, and we're going to try to decide which ones are oxidation reduction and which ones are not. Now, I've got a rule of thumb that'll help you. Right? If the only question is which one is redox, the rule of thumb can shorten the decision time. So here we have these three. All right. The rule of thumb. If you have an element on one side of the arrow, either a reactant or a product, and on the other side of the arrow, that element is in a compound, then you have a redox every time. So for this one, there's the element zinc, it's in a compound over here. There's the element hydrogen, it came from a compound. So that's definitive. That is a redox reaction. You got another one down here. Okay. Copper is in this compound, and it's an element over here. That's a redox reaction also. Now, for this one, there's no rule of thumb. You have to calculate that one and determine what are its characteristics. But we're going to have to do each one of them. Why? Because the question says, identify the reactions as redox or not, and then decide which one is the oxidizing agent and which one is the reducing agent. Okay, so we're going to have to do each one anyhow. All right, A. Let's see, we got zinc. I'm going to leave out the phases because we don't need them to do the calculations. HCl, chlorine, and hydrogen gas. Okay, so this one's 0. I'll do the elements first, they're the easiest ones. That one's 0. This one's a +1. This one's a -1. This one's a -1. Right? We have to use that assumption again. Chlorine will be -1 here. That means zinc has to be +2. Okay? So that confirms that we have a redox reaction. Zinc went from 0 to +2. It was oxidized, which makes it the reducing agent. Okay? Because it reduced hydrogen from a +1 to a 0. Right? That makes hydrogen the oxidizing agent. Okay? About this one? Let's see, dichromate. And hydroxide. And chromate. And water. Okay, we don't have any elements here, so we'll go to our other rules. That's -2 for oxygen, +1 for hydrogen, -2 for this oxygen, and -2 for this one, +1 for that one. And this one's a -2. So let's start with this one. That means 7 times -2 is -14, but we're going to hold 2 of those charges out for this one. Right? 12 is all we have to balance. So that means +12 for those 2 chromiums, which means +6. Okay? How about this chromium? Well, let's see. 4 times -2 is -8, but we need to hold out 2 for that negative. We only need to balance 6 minuses. That makes this one +6. Okay. Now, what can we deduce from this? This is not a redox reaction. So, since this is not a redox reaction, we don't have any oxidizing agents. We don't have any reducing agents. And then the last one. We know this one's a redox. We just need to deduce what are the oxidation states. So this one yields that one plus that one. That's a 0. We're going to give chlorine a -1. That makes this one a +2. We're going to give this one a -1. That makes this one a +1. Okay. So what's going on here? This copper went 2 different directions. Right? This +1 became a +2. It was oxidized. This +1 also became a 0. It was reduced. So sometimes it might be better in this case to say, like that. This would be a -1 +1. -1 +1. Okay? Instead of putting the 2 in front of 1 formula, we just break it into 2 formulas because we know they're going to go 2 different directions. So let's say this one goes here. So it is oxidized. It has a loss of 1 electron per copper times 1 equals 1 electron. This one has a gain of 1 electron per copper times 1 equals 1 electron. So the electrons balance. This one is reduced, which makes it the oxidizing agent. And that makes this one the reducing agent. Okay? This reaction has a special name. It's called disproportion reaction. Simply because we went 2 directions from the same location. In reality, 1 copper compound did one thing and another copper compound did the other. So we're not saying that it's got a split personality. This one just went that, and it doesn't matter which one went where. Okay. So we fill in the information here, and that's a redox. That one is the reducing agent because it's red. Yep. And that's the oxidizing agent because it's blue. We determined that this one is not a redox reaction, so we can let it go and move on to C. Right? Copper 1 chloride is the reducing agent. It's also the oxidizing agent. Okay? All righty then. All right, now we're going to look at how do you balance a redox reaction. If you're given the reactants and the products, then what's the best way to balance a redox reaction? Up to now, we just balanced using molecular methods in my budgeting scheme. If you know that you have a redox reaction, this works best. Now, you can do it, and I'm going to show you the method for splitting your reaction into two half reactions. One is the oxidation reaction, and one is the reduction reaction. And then you balance those, and you reconcile your electrons between the two, and then you put them back together. Sometimes you don't have to do that. Sometimes you can balance just straight, just by doing the electrons first and then doing the molecular budget afterwards. But this is a surefire way. If you're ever in doubt, you can go straight to half reactions. And it will always work. So we take the given reaction, which should not be balanced, and we decide what is the oxidation half and what's the reduction half, and split them into two equations, and then balance them for electrons in the beginning before you combine them. Okay? Here's an example. Notice that we don't have a balance in charges on either side. This is like the tin example earlier, the tin and the iron example. We've left out the spectators. So what we have here is protons, which are probably from hydronium. And then we have a manganate, not an ion, but a manganese 4 oxide compound. And then we also have iron 2 plus. On the product side, instead of 4 plus now, we have 2 plus manganese. So something happened to manganese. And the iron went from 2 plus to 3 plus. And we ended up, from this hydrogen, we ended up with a water molecule. Okay? So the first thing you do is determine which one is oxidation and which one's reduction. So we need the oxidation states on each one of our elements. There you go. There you go. So now we've got all the oxidation states. And we did that just like we always do. Use our rules. And we're going to split it into the reduction. So which one's the reduction reaction? Which one gained electrons? Well, let's see. It looks like manganese gained 5 electrons for each atom of manganese. So that's the reduction reaction. Manganese, this compound goes to that element. And that's not the whole story, but these are the players for the reduction reaction. We do the same thing for the oxidation reaction. Well, I think I need to work on this slide. Let's do it this way. Let's set up our reduction. We have manganese, oxide, manganate ion, excuse me, and then it's going to that one. We're going from +7 to +2. Okay. Hold on just a second. All right. I'm gonna breeze through this one right now because it's using rules that we haven't defined yet. So I'm just showing you this. These are the main players for the reduction. Right? And it's going to have oxygen over here simply because there's oxygen on this side. There has to be oxygen on that side. And now we have hydrogens. We have 5 electrons. That accounts for the reduction. And notice the reduction, the electrons go on this side because they're going to be added into this manganese to make that manganese. And this one, the oxidation players are iron 2+ going to iron 3+. Okay, so now let me give you some guidance, some rules. We know that we have to split the reaction into 2 separate reactions, oxidation and reduction. There are 2 approaches to balancing by the half reaction method. Actually, there are 3. The null situation, the 0 method selection, is if you have no acid, no base, or you have no oxygen and no hydrogen involved. You don't have a pH change. In that case, you can do the half reaction without introducing oxygen or hydrogen to make water. But if the problem says you're balancing in acidic solution, then you approach it the way we're going to do it first. If it says you're in the basic solution, then we're going to do the acidic first anyway, and then change it to basic afterwards. That's the most efficient way to do it. So now we're just going to look at the acidic solution method for half reactions. Okay. We've gotten through this one. Identify and write the equations for each half reaction, oxidation, reduction. Then, actually, I think these are out of order. I prefer to balance the electrons first. Make sure that you've got the electrons accounted for as either reduction on the reactant side, or in the oxidation step, they would be on the product side. And then you go and balance all the elements. Actually, do all the elements first. I think that would be better. Balance all the elements except hydrogen and oxygen. Don't do them yet. Then do your electrons. And then once you get the electrons balanced, balance the oxygens using water. So if you have oxygen on the reactant side, you put water on the product side for the same number of oxygens. Now, since you put water on the one side, then the other side has to have some hydrogens added, and you add those as H+, protons. That's where the acid method comes in. This will make a whole lot more sense when I show you an example. Okay, now it will work with those steps just like they are, but personal preference, I like to get the electrons in there a little earlier. Okay, let's see, we have an example. Oh no, we're not finished. That balances the oxidation and the reduction steps. Then what you have to do is be sure that the same number of electrons that go into the oxidation step or come out of the oxidation step go into the reduction step. Got to balance the electrons. And you do that with a coefficient multiplied by the entire equation. Once you get the electrons balanced, then you can add the two back together. And in that case, the electrons will cancel out. Because in one reaction, you have the same number of electrons on the product side, and in the other one, you have the same number of electrons on the reactant side, and they cancel. So in your composite equation, you won't have any electrons showing. And then you reduce it. And I'll show you what that means in a minute. Okay. So here's our example. Let's see, how much room do I have on the board? Squeeze it over here, maybe. CR2O7 plus SO3, 2 minus. That's the sulfite ion. Chromium 3 plus. And sulfate ion. Okay. Now we have to decide, let's see. Yeah, I'm good. Now we have to decide which one's which. Which one's the oxidation step? And then which one's the reduction step? Well, let's see. That one's 3 plus. This one's 2 minus, which means 8 minus for oxygen. Hold out 2 minuses for that. That means sulfur has to be plus 6. This one is 6 minus total for the oxygen. Right, the oxygen is 2 minus, but we have to hold out 2 minuses for that, so we only need to balance a minus 4. So that sulfur is plus 4. This chromium, we did this chromium earlier. That's a plus 6. Okay. So now we have our oxidation states. We can decide which one's which one's oxidized, which one lost electrons, had an increase in oxidation state. Sulfur went from plus 4 to plus 6. So that means sulfite, I'm going to put this up here just so we can keep track of it, goes to sulfate. Okay, that's our oxidation. So our reduction must be dichromate with a plus 6 on the chromium, and this to chromium 3 plus ion. Okay, that's our reduction. Okay, so let's see. Yeah, maybe we will. We'll go ahead with the oxygens. Well, we balance the non-oxygen, non-chromium. So this one has 2 chromiums on that side. We need 2 on this side. You know? 1 sulfur, 2 chromium, 2 chromium. Okay, now we can balance the, I'll stick to the rules the way they're written. We have 1 oxygen on this side, 4 and 3 on this side, 4 on that side. We need 1 more oxygen. Right, so there's an oxygen, makes 4. But we've added 2 hydrogens. So now we need 2 hydrogens. Okay? On this side, we've got 7 oxygens. So we need 7 water. But that added 14 hydrogens over here. So we need 14 hydrogens. Okay? Now we balance the electrons. So we went from plus 4 to plus 6. That's oxidation, which means these electrons are going to be over here. You had to lose 2 electrons, and loss of electrons puts the electrons on the product side. Gain of electrons puts the electrons on the reactant side. We went from plus 6 to 3 plus, which is 3 electrons for each chromium. but we have 2 chromiums. So that means 6 electrons are required on this side. Okay? Now, we need to reconcile the 2. This one has 6 electrons, that one only has 2. We need to make this one 6 electrons. So we're going to multiply by 3. Okay? So that makes this 3. That makes this 3. 3, 6, and 6. Okay? Now we can combine them. So let's try to put them in the same order that we have them up here. So we'll put the chromate first. Let me see them. I don't want to slide off the edge of my board and start to just get chopped off. So I better move it over here. So I'm going to do chromium first. Okay. And then I'm going to do sulfite, which is 3 of them. Okay. Then we've got 3 waters and 14 hydrogens. Okay, that accounts for everything on this side. All these right here. Notice I didn't put the electrons here because those 6 cancel these 6. We don't need them. On this side, we're going to start with the 2 chromiums, 3 plus. Then we're going to have sulfate. I'm going to have to move down here. 3 sulfates there. Okay. Then what do we have left over? Well, let's see. Let's put the water next. 7 water. And then 6 hydrogens. Okay. Is that everything? We have 1, 2, 3, 4. 1, 2, 3, 4. And we have 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's everybody. Now you can reconcile duplications. We have 3 waters on this side. We have 7 waters on that side. So all of these 3 waters go. And that leaves us with 4 waters on that side. We have 14 hydrogens on this side and 6 on that side. So these hydrogens go, and now we're left with 8 hydrogens. So we should have dichromate, 3 sulfites, 8 hydrogen, 2 chromium 3 plus, 3 sulfate, and 4 waters. Oh, okay. So you're going to get an animated step-by-step here instead of doing it that way. But I found that students like to see it this way. So this is just sort of reinforcement. Okay. The next slide. There we go. So far, so good. Okay. So did I skip a step? No, we're good. The next slide, we're going to reconcile the electrons. Notice here we've got 6 in this one, 2 in that one, just like before, and I'm missing my negative sign on the electron. Multiply by 3. Now we can add the 2 equations together. Okay, let's see. There's the dichromate. There's the 3 sulfites. There's the 8 hydrogens. There's the 4 waters, 2 chromium 3 pluses, and 3 sulfates. Okay, that's how you do it. You just have to be very methodical about the whole process and practice. That's why, let me see, how many of these did I give you? That's why the reviews, I gave you 91 problems. I doubt in 2 days that you're going to get them all done, but there's lots of practice in there for you, however many you can get done. Okay, when the reaction series.
Which assignment is that one?
I'm sorry?
I said, which assignment is that one, like the 90 problems?
Oh, that's your review document. That's not the homework. That's the review document that gives you lots of practice.
Is our test not next Tuesday?
A week from today.
Oh, okay.
Yeah. So next Thursday, we'll come back and we'll go through some of these problems. And hopefully you will have looked at some of them. And if you have any issues, we can deal with them at that time. Okay, cerium, 2+ charge, cobalt, 2+ charge. We end up with cerium 3+ and elemental cobalt. So this is definitely a redox reaction. What's the coefficient in front of cerium 2+? This is one of those cases where we don't need to separate into half reactions. We can, but we don't have to, right? Because there's no oxygen there, there's no hydrogen there. All we have to account for is these elements and the electrons. So this method is sort of an abbreviated version that works fine. Cerium 2+, cobalt 2+, cerium 3+, and cobalt. So that's a 0, and these are all charges. So which one went where? Well, the cerium lost an electron. 1 electron per cerium. Cobalt gained 2 electrons per cobalt. Right? So we've got 1 electron here and 2 electrons there. How are we going to deal with this? Well, we need 2 electrons up here, right? To balance those 2. So we need to multiply by 2 to give us 2 electrons. That means we need a 2 here, 2 there. And that will give us balanced electrons and balanced equation. Coefficient in front of cerium 2+, cerium 2+ is a 2. Okay? So we didn't have to split this one into half reactions in order to get the answer. This one definitely needs to be half reaction. Notice that we've got bromine going from, there's a minus sign in here, it's really hard to see. We're going from a -1 to a 0, and here we're going from a manganese 6. Let's see. 7, excuse me. Manganese 7 to a manganese 2+. So that one is reduced, and bromine is oxidized. And we know we need to go half reaction method because, well, 2 clues actually. The problem says in acidic solution. That's a giveaway there. Plus, we've got oxygens here. Right? Oxygen on the other side and no oxygen on the other side. So you're going to have to deal with that oxygen somehow. And the half reaction is the way to do it. Right? So this is the reduction. We've identified the reduced species. And then we need the oxidation. There you go. Next, we want to balance all the elements except hydrogen and oxygen. Reduction is no problem. There's one manganese on both sides. Bromine, we needed two bromine ions and one bromine molecule. Okay. Then we're going to balance the electrons. So 5 electrons for each manganese, we only have one of them, will get us from +7 to +2. That's a reduction. Oxidation means that we need 2 electrons because there's 1 electron for each bromine that had to be lost. So with 2 bromines, that means we need 2 electrons here. Now the oxygen atoms have to be balanced out with water. So we put water on the product side. There we go. But we need 4 of them, don't we? We need 4 oxygens. There we go, 4 oxygens. So that gave us 8 hydrogens that need to go on the reactant side. There we go. 8 hydrogens. Now, next, balance the electrons. In this case, we've got an odd prime number and an even. So you can't just use a multiplier for one reaction and get it balanced. You got to use a multiplier for one and a different multiplier for the other in order to come out with the same number of electrons. So when you have a situation like this, the best way to deal with it is cross multiply. What I mean by that is this one's 2, so we multiply this one by 2, this one's 5, we multiply that one by 5. And that'll give us 10 electrons total in each equation. Okay. So there's your 2 that came from down here, here, and your 5 goes down here. And we end up with these 2 modified equations with equal numbers of electrons. Now we just have to add them together and reconcile any redundancies. Well, in this case, I skipped a step. We did the reconciliation in this case. No, in this case. We got rid of the electrons. And then we found out that we didn't have any extra waters on either side. We didn't have any extra hydrogens on either side. So we're done. Now, what if we had said this reaction is balanced for basic solution? You go through the acid balancing technique, then you take your balanced acid solution equation and change it into base. So how do we do that? You have to neutralize the acid. And how do we neutralize acid? We use this equation. Let me get this off here. It's not confusing. If you have hydrogen ions on one side, then the way to neutralize them is to combine them with hydroxyls. Make water. Okay? But if you add hydroxyl on one side, you got to add hydroxyl on the other side. So in this case, we're going to add, how many hydroxyls will combine with these hydrogens? 16. Right? 16 OHs and 16 H pluses will give you 16 waters. So we're going to add OH on this side and OH on that side. Okay, here we go. 16 hydroxyls, that will neutralize the acid, but we have to put those 16 over here also. Okay, because we're balancing. So that gives us 16 waters over here against 8 waters over there. Right? So we're going to have to reconcile that. Okay. This just brings everything down at once. I should have chained these together so I wouldn't have to click each one. And then there's your hydroxyls. Now we got to get rid of 8 of these waters and all of those waters. There you go. So that will that's your balanced equation in basic solution. Okay. So now that we learned how to balance equations, balance redox equations, we're going to look at what are the implications for redox reactions. And that leads us to the topic of electrochemistry. Electrochemistry is the study of the interchange between chemical and electrical energy. And it always takes place with the transfer of electrons. That's how the energy transfers through the electrons. We can look at this in 2 ways. If you put reactants together and they spontaneously react by transferring electrons, then you have a galvanic situation. I can't say a galvanic cell yet. We have to qualify that. But you have the potential for extracting energy from the process because it's spontaneous. The electrons are going to move whether you're there or not. The other is if you want the reaction to run in reverse, then you pump electrons into it and force the oxidation to go backwards as a reduction, and vice versa. Those are the 2 possibilities. Okay, for the galvanic situation, we form an electrochemical cell. Notice that up to this point, our reactions have been all in one equation, except when we separated them to balance them as half reactions. So for this reaction, which is balanced for our convenience, well, actually, the whole reaction would be all this together. This would be the oxidation step. This would be the reduction step. And if we put them together in a single container, the electrons will transfer, but we will not have access to them. We can't gain any work from them. We can't gain access to those moving electrons at all. What we do in an electrochemical cell is we separate the half reactions into half cells. And the only way that electrons can be transferred is through an external route, right here, through that wire. That's where we tap the electrons and extract energy from the reaction. Now, we usually put, let's see, well, we do separate the half reactions into separate containers, half cells. So here we have iron 2 plus, but we also have iron 3 plus in there. And here we have manganate ion in acidic solution. And we need manganese 2 plus also in that solution. So in this case, the electrodes, these solids here, they don't participate in the reaction. The reaction is entirely in solution. The electrodes are there just to collect the electrons and send them from one to the other. So which way are the electrons going to travel? That's the key. If this is the electron donor, the reducing agent, then electrons are going to be removed from that iron and sent through the wire and leave an iron 3 plus behind. So the electrons are going to move from right to left. And when they get over here, they're going to be added to that manganese to make this manganese 2 plus also in solution. Okay, so the electron movement is this way, from that half cell to that half cell. There's just one problem. You can't move electrons in a broken circuit. You have to have a complete circuit before electrons will move. That's just a physical law that every electrician knows. So this is incomplete. In order for those electrons to move, we need a way for the current to flow in a circuit. So what we have to do is connect this half cell to this half cell through some sort of external ion transmitter. There are several ways you can do it. Right? One way is to make a salt bridge. It's just a tube filled with a solution of ions. And they need to be common ions to the mixtures. Most of the time, it works best. You can either plug the ends so that you don't get wholesale mixing, or you can mix your ions into a gel, like agar. If you've got any microbiology, you know what agar is. It's that stuff you pour into plates and into tubes and let it cool down and it sets up solid. That way you don't get any movement into the solution, except for the free ions. Or you can put a porous disc between the two. And that keeps wholesale mixing from happening. There are sometimes you can do like this and have a ceramic cup. This ceramic cup, then your ions can move back and forth, and you have this one is right, one cell, and this one is the other cell. Okay, that works also. Okay. A galvanic cell, an electrochemical cell, these are interchangeable terms. They're also known as a battery. Batteries, when they're fully charged, will deliver energy externally through their contacts. And in this case, what we have is electrons moving out here and exchange of ions here to balance the charges. That's the only purpose. Well, complete the circuit, but at the same time, they're balancing charges. Because in a battery, in electrochemistry, we don't have any unbalanced charges. There are no static charges. Okay. Now, we have some terminology that needs to be explained. One electrode is called the anode, and that's where oxidation occurs. Oxidation is occurring here. In other words, electrons are being removed. Oh, I hate when that happens. Forgot to plug in my battery. Speaking of batteries. Okay, back to the topic. The anode is where oxidation occurs. In other words, electrons are leaving that cell through the external circuit. The electrons are being donated by the anode through the wire to the cathode. The cathode is where reduction occurs. So we get reduction over here. So the anode supplies electrons externally to the cathode so that reduction can occur. All right, so that was one type of electrochemistry where the reaction occurs spontaneously, and by separating the half reactions into separate cells, we can access that energy, that spontaneous release of energy for the reaction. But if we want it to go the other direction, or reverse the reaction, we have to supply electrons with sufficient push voltage to drive the reaction backwards. And that's electrolysis. And electrolysis is just as important as the electrochemical cells. Oops, went backwards, sorry. Here we go. So in this case, the reaction that we want is not spontaneous. We have to provide an external drive to make the reaction go backwards. And that happens when you start your car every morning, or whenever you start it. The battery under the hood is operating as an electrochemical galvanic cell. It's providing energy through an external circuit to the starter attached to your crankshaft, spins the engine, and it also provides energy to the ignition system. And that drains some of the energy from the battery. Once the engine starts and the alternator is turning, it sends electrons back through the battery and drives the reaction backwards. Then the battery is acting as an electrolytic cell. It's being charged, running the reaction backwards. So that the next time you want to start your car, there's energy there to do it. Other types of electrolysis, if you've ever seen vintage automobiles, they might have chromed bumpers. Right? None of this colored plastic stuff on hydraulic pistons. They're solid chrome bumpers. They're chromed by this process. Normally, chromium wants to react and become oxidized. But when we want to put it on a bumper, we run the reaction in reverse and make the chromium ions, we reduce the chromium ions into metals, right? The chromium ions are positively charged. We add electrons to them by forcing them, and that makes chromium metal, and it deposits on the bumper. Because the bumper now is the cathode. That's the site of reduction. I used to have a bicycle as a kid. It had a chrome-plated frame. It was pretty sharp. And that's how they did it. They added chrome by electrolysis. The nice thing about chrome on steel is it protects the steel. Right? It won't rust as long as you chrome every surface. Don't let water or oxygen in. Chromium will protect it. Besides that, it shines. Okay, this was the battery that's under the hood of your car. Most cars. I guess some the hybrids now, they have lithium-ion batteries instead. But this is the lead storage battery that all internal combustion engine only cars have. The anode reaction, the oxidation takes place where lead in one plate of your battery. So you have lead. That's wrong. Lead. There we go. You have lead here is submerged in sulfuric acid. So there you have your lead, there you have your sulfuric acid, and this lead undergoes oxidation, right? It loses electrons, so that means the electrons are flowing out. Okay? So as it loses electrons, it becomes lead 2 sulfate deposited on the surface of that plate, because lead 2 sulfate is not soluble, even in strong acid. So it's deposited on the surface of the plate as it reacts and picks up sulfate from the sulfuric acid. So where do those electrons go? Well, they go to the cathode. So there's another plate over here that's made of lead oxide. So this had a 0 oxidation state. This one has a 2+ oxidation state. This one has a, let's see, excuse me, 4+. There we go. I knew that didn't add up. 4+ for the lead oxide. This one's a 2+. The lead oxide also reacts with the sulfuric acid and produces lead sulfate with 2+ charge. So the electrons go over here and reduce that lead in the plate to lead sulfate by this reaction. And then, since both plates are submerged in the same solution, you don't need a bridge. Right? That's the beauty of the lead acid battery. One of the things is you don't need a salt bridge or any type of barrier, because all of this is common. Okay, so that is one cell in your lead storage battery under your hood. If you take a peek at it, you'll find that there are 1, 2, 3, 4, 5, 6 cells in that one battery. Okay? So each one of these cells produces 2 volts. Right? So one of the laws of physics, of electricity, is if you chain these together, if I have to take another cell over here, and I have a lead right here, and let's see, how does that work? We got another lead oxide here. We need to chain these over like that. And just keep going. So there's 1 cell, 2 cells, you need 4 more cells. When you chain the cells together in series, you'll get 6 times 2 is 12 volts. That's why the battery under your hood is a 12-volt battery. Okay. So that's the reaction that takes place in your battery, and it produces lead 2 sulfate on both plates. So when we run the reaction backwards, it takes this lead and makes lead oxide out of it again. It releases the sulfate back into solution. And this one, it takes this lead sulfate and converts it to lead and also releases the sulfate back into solution. When we run it backwards as an electrolytic cell, when the alternator is charging your battery, it just runs that reaction backwards. Okay, there's the overall reaction. And you probably never heard this term, but it used to be pretty common when I was growing up. When a lead battery has reached the end of its life, in other words, it's gone through discharge, recharge, hundreds of times. What happens is it gradually builds up that lead sulfate on the surface of the plate, and it leaves enough of it there that it occludes the surface so that no more of this lead can react with sulfuric acid, or no more of that lead oxide can react with sulfuric acid. And at that point, your battery's dead. It has no access to the solution underneath, to the solution in which it's submerged. And at that point, we say it's sulfated out. So the physical design of these batteries is important for their number of cycles and long life, and not just the voltage, but how many amps can they produce. And the amperage is a function of surface area. If you have a large surface area, you can produce more amps with the same voltage. And one thing you don't want to do is reach in there and grab both poles of your battery, because it'll hit you with about between 200 and 300 amps, and it will knock you down if it doesn't kill you. Okay, oops, wrong direction. So there's no need for a salt bridge. And when you get sufficient lead to sulfate accumulated on the plates, then your battery's dead. Or if you've got a good design in your battery, you may be able to completely use up the plate. In any event, recharging it won't work. It has to be recycled. Okay, I mentioned voltage here, 2 volts per cell. That's also known as electrical potential. And this can be viewed as a pressure or a push behind the electrons. So the push to move these electrons from here to here is 2 volts. Some electrochemical cells, galvanic cells, will produce fractions of a volt. 2 is about as high as you can get. You can go a little bit higher, but 2 is pretty good. That's another reason that the lead acid battery is popular. I mean, they're heavy, but if weight's not an issue, then they're very, very good vessels for storing energy and for delivering a lot of energy quickly. Okay. So that's not the only type of battery. You can buy D cells, C cells, AA's, AAA's, those are the most common ones. Dry cell batteries off the grocery shelf, and they use a different set of half reactions to produce their 1.5 volts. So you'll notice that the D cells, the C cells, AA's, the AAA's, they all produce 1.5 volts. They're rated at 1.5 volts. So it's the same chemical reaction in each one. The difference is size. So you'll notice that the D cells are big. They will last a lot longer. They've got more material in there to react before they go dead. Whereas the little bitty ones, the AAA's, don't last very long. Okay, and you can get different versions, right? Remember we talked about balancing the equation in acid solution or basic solution? Well, you can get the same thing with dry cells. You can get the acid version. Well, here's the dry cells that I was talking about, the D's, the C's, the AA's, AAA's. That's a different reaction. This is a zinc cell. The anode for the zinc cell is zinc metal goes to zinc 2+. So that's the oxidation step, the anode. That delivers the electrons to the external circuit. So that would be the negative pole of the battery. That's where the electrons come out of the battery. No, this is the dry cell. This is the one you see on the grocer's shelf. My mistake. One version. And the reduction side is this one. So these electrons go in here, they go external, then they go to the positive pole of your battery and finish off this reaction. The reason they're called dry cells is they don't have a liquid electrolyte. What they have is sort of a paste. It's an absorbed liquid. Easier to handle, less likely to spill. There's an alkaline version also, which also uses zinc, but this one is in basic environment, hydroxyls. In the case of the dry cell that you find on your grocer's shelf, the anode, the point of oxidation, right, produces the electrons, is part of the case of the battery, the zinc casing, and it's also got a clad around the outside, so it won't short. And these electrons flow out through the negative terminal here. Oh, excuse me. No, they flow out through the base plate. This negative is terminal, this graphite rod is isolated from that. So the electrons flow out this way, flow out this way, go out to do work, and then they come back in here. And that graphite rod is there simply as a conductor. It does not participate in the reaction. All the reaction for the cathode occurs in the paste. And the anode reaction occurs at the site of the zinc casing. Okay, so let's see. Other types of batteries. Silver cells. These are very common for calculator batteries and hearing aid batteries. The mercury cell, which is not used anymore because of the mercury, is also used in usually small applications, very small batteries. But they're packaged in such a way that one side of the battery is the electrons out from the anode, and the other side end is the cathode's in, positive pole. Nickel cadmium. These, so up to this point, we've talked about non-rechargeable batteries. Now, for a while, they were marketing a device that would recharge your dry cell batteries, but they were not very efficient, and you had a limited, you might get 20 or 30 recharge cycles out of your battery before it was useless. But some batteries can be made engineered to be rechargeable. In other words, they work very well when you drive the reaction backwards. And the nickel cadmium battery was one of those. In fact, I used to have a trimmer, beard trimmer, hair trimmer, that had built-in nickel cadmium battery. and you could recharge it. The problem with the nickel cadmiums was they had memory. If you let the battery discharge completely all the way till it's dead and the razor's not working anymore, then you recharge it. Then it remembers that it was at 0 at one time. That is its 0 point. And when you recharge it, it'll have all that energy available to go all the way to 0 again. If you discharge it halfway and then recharge it, then it thinks that new level, only half charged, is the new 0 point. So it'll go down to that 0 and stop. That was the bad thing about nickel cadmium. Aside from the cadmium, which is toxic. And so we don't use that very much anymore. Now, here's a topic. Oh, corrosion. Corrosion is just another word for electrochemistry. When a metal corrodes, it is undergoing a redox reaction. And it's going from metal, usually to the oxide, sometimes the sulfide or some other, but it's being oxidized. The metal is being oxidized. It's losing its electrons and losing its structural integrity. I mean, it's only good if it's as a metal. So one way to protect those metals, like this buried pipe, is to connect them with a wire to another metal that corrodes more readily than the metal that you're protecting. It's called cathodic protection. So what we do is we connect this pipe with a wire to magnesium that's buried in the soil. The magnesium corrodes. It becomes the anode. It produces electrons in that wire. So as it corrodes, it sends electrons up here through the pipe and keeps the pipe reduced. Okay? The key to that is finding a metal that corrodes more easily, that is oxidized more easily than the metal you want to protect. So all ocean-going vessels, all ships, have steel hulls. And the way they're protected is they have a strap around them below the waterline that's made of zinc. And it's riveted to the steel hull. The zinc will corrode and send electrons into the hull and keep the steel from corroding. If the engines are running on the ship, then it trickles a direct current, a direct charge, electrons, into the zinc. And that keeps both the zinc and the iron in the steel hull from corroding, as long as the engines are running. But when they're docked, then the zinc does its job and usually doesn't corrode very much because the ships are only in the dock for a day or two. And then they crank up the engines, or actually they could run batteries, right? Batteries inside the ship and run a trickle into the zinc. And the zinc is there as a go-between. It's a protector. It's a cathodic protector. Okay. So that's one way to protect the pipe, the steel pipe. Another way is to put some kind of coating on it, right? If oxygen can't get to it, if the elements can't get to it, then it won't corrode. So sometimes you'll see pipe wrapped in some type of material. Used to be petroleum-based. Now they can do it with plastics. Well, that's petroleum-based too. I mean, it's like like a thick grease, fabric. But now they can wrap them in plastics. Or you can make an alloy. Right? You can put the cathodic protection in the metal. That's what stainless steel does. Originally, stainless steel was 35% chromium. It's lower now because they found you don't need that much. But the chromium oxidizes instantly, right? Exposed. If you have a stainless steel, whatever, knife blade, for instance, and you scratch it, the chromium in that steel will instantly form chromium oxide and seal the wound. So the iron will never corrode. That's alloying. And then the cathodic protection that I previously described. Those are ways to protect. Coatings. You don't have to coat the metal in plastic. You can coat it in the metal that you want to protect it, like zinc. You ever seen I don't know, they might still sell them in some hardware stores, galvanized buckets. They're dipped in molten zinc. So you get zinc coating on your bucket and it keeps your bucket from rusting. Okay. So in this case, the buried pipe for the cathodic protection, the buried pipe is the cathode. And in this case, the magnesium chunk is the anode. So it seems like you call it anodic protection, but no. Somebody called it cathodic protection and it stuck. So we have to call it that now. Okay, electrolysis. If you force a current through some materials, you'll get a reaction. The spontaneous reaction, in this case, would be oxygen gas and hydrogen gas combining, set them on fire, and they burn. They're very energetic. That's how we used to get the space shuttle up in space. It burned liquid oxygen and liquid hydrogen. But if you want it to go in the reverse, you've got to put energy in. So if we put energy in, we can split the water molecule into hydrogen and oxygen. Okay. That's the way nuclear submarines can stay submerged for so long. First of all, they take seawater and use the ample energy from their nuclear reactors to distill the water. So they get pure water for drinking and bathing and cooking purposes. And then they take some of that pure water and they run an electric current through it and make oxygen. And that's where they get their breathable air. They scrub out the carbon dioxide with probably potassium hydroxide, lithium hydroxide. Take the carbon dioxide out and replace it with oxygen from this process. And they can stay submerged for months. Here's one of the dangers. Used to be older lead acid batteries under the hood of your car had in their caps, they had little holes in them. Those holes were in there to let hydrogen gas out. Because once you start charging that battery, if you overcharge it, if you go too far, then it will start electrolyzing the water in the solution and making hydrogen gas and oxygen gas. So if you trap it in there and you build up enough heat or a spark, whatever it takes, you can blow that battery up, catch it on fire. But now they have special materials that are incorporated in the battery that if we produce any hydrogen from overcharging, then those materials absorb the hydrogen and inactivate. So now you can get sealed lead acid batteries for various applications like uninterruptible power supplies for your computers. Those little things that sit on the floor If your power goes out, then they keep your computer running until you can shut it down without loss of data. Those batteries in there are sealed. They're epoxy sealed. There's no way to get in or out of them. They have within them that material that absorbs the hydrogen and keeps them safe. Okay. This process of electrolyzing water is often considered the holy grail of sustainable energy production. What you need is a cheap, non-polluting source of energy. Wind power, solar power, they don't fit the bill. They're too intermittent, they're too diffuse. You'd have to cover the entire earth with wind turbines and solar panels to meet the world's needs. But nuclear power, it doesn't generate any chemical pollutants at all. But it produces abundant sources of energy. If you can take all that excess energy and split the water molecule into hydrogen and oxygen, then keep the hydrogen, and that's your energy source. All you need now is to run it through, you could either combust it, or you could run it through a battery, a fuel cell, and you could regain that energy from it. And that way, you start out with water, you go here, and you run it backwards, and you end up with water. So it's just a cycle. The only thing that's running through it is energy. Oh, okay. End of discussion. Any questions? Got a couple minutes to go. Okay. In that case, we'll see you on Thursday, and we'll take a look at these review problems.